everybody. My name is Bethia. I am a geography educator. I've taught it for a number of years. I'm passionate about it, but I'm also passionate about helping learners understand basic concepts in geography. And so for the purpose of this video, it's to explain the characteristics and distribution of mid-latitude cyclones. And in the next video, I would like to talk about the formation of mid-latitude cyclones. So if we have a look at this image here, you can see a mid-latitude cyclone that is moving across South Africa. This would be bringing quite severe weather. So if we have a look here, this would be the type of weather it's bringing. You got windy weather, might have snow, heavy rain, large waves, and even flooding. And these characteristics are due to pressure, wind patterns, and different air masses that are involved in the formation of a mid-latitude cyclone. So mid-latitude cyclones are low pressure cells. So I've made a low pressure cell here for you to have a look at. It has got an L in the center, so you know that it is low pressure. And if it was high pressure, you would have an H on the side. So low pressure also means that the isobars have got lower pressure in the center and it's going to have higher pressure on the side. So we've got 992 in the center and 1000 on the side. If the hectopascals is lower than 1000, it's generally considered low pressure. Okay. So this is the winds that would blow into a low pressure cell in the southern hemisphere. So they have mid-latitude cyclones, as we said, is a low pressure cell. It's going to have converging winds that would blow into it. So converging means to come together. So these winds are coming together into the low pressure cell. And an important thing to remember is that they're going to blow clockwise in the southern hemisphere. Okay, there we go. In the northern hemisphere, it's the same principle applies, except they blow anti-clockwise. And the reason that the winds do not blow just across the gradient force like this, or over here, and why they are deflected, or they blow in a circular pattern, is due to the Coriolis force. So it's the force that causes the deflection of moving objects due to the rotation of the Earth on its axis. So if you can't remember, not sure what Coriolis force is, go have a look at the grade 11 workbooks, textbooks, or just YouTube a couple of videos. There are very good videos out there that will be able to help you and explain things nicely to you. Alright, I've included a side view of a low pressure cell because often we have a look at the top view and you think, what's going on here? But this is what it looks like on the side. So the converging winds that are coming together would blow in here at the bottom, and it would normally be warmer air that is blowing in. So warm air rises, and then once it starts to reach dew point, you're going to have condensation taking place, formation of clouds, and then you're going to have rain. Alright, so yet again, the converging winds blow in here from the bottom, and they blow, the air moves upwards until it reaches dew point, where it's condensation, formation of clouds, and therefore rain. Okay. So on this picture of the Earth here, we have 0 degrees latitude, 30 degrees, 60 degrees. And the mid-latitude cyclones form in the middle latitude. So they're going to form here in the southern hemisphere, and they're going to form here in the northern hemisphere. So they form roughly between 30 and 60 degrees north and south of the equator. So you're going to have them over here. Okay, so you should remember, hopefully, the different cells. You have the Hadley cells here, you have the Ferrel cells here, and you have the polar cells. So Hadley, Ferrel, and polar cells here. So the mid-latitude cyclones form in the Ferrel cells, over here. Yet they form along the polar front. So the polar front is an area or line that separates two different air masses. So a warm air mass here and a cold air mass here. All right. So what happens here is that you have the warm air mass gets lifted up. So these westerlies would get lifted up because it's warm air, and the polar easterlies would wedge in underneath. Show you in the next slide. There we go. So this is your front. Okay, this is a cold front, but yet again, it could be used as the same principle as a polar front. This is your cold air here, and this is your warm air here. So your warm air is being lifted up, and then your cold air is wedging in underneath. As your warm air lifts up, your temperature drops. You're going to have condensation, clouds, and therefore it's going to rain. Okay, so basically your warm air is going to start dissipating, and then your cold air is moving in this direction. Okay, all right, here is a picture from the textbook. I've had to zoom in on it or enlarge it, and that's why it's rather blurry, but you get the gist of it. So it's of a synoptic weather map, if you will. So this is the low pressure cells here. So these are your mid-latitude cyclones, and this is the cold front here. So the cold front is the line that's going to separate your warm sector from your cold sector. So the way I remember what's the cold front is the little icicles. These little points here are associated with icicles for winter, and then this is your warm front here, which is going to be which is associated with like half moons or half suns, which is hot. So that would be warm, and that is cold. So the warm fronts are bent southwards, so they are bent away from South Africa, and these are pointed towards South Africa. So I always look at where they are pointed along the whole line to indicate the direction that they're moving in. So these would essentially point the direction that they are moving in. All right. Here is a synoptic weather map with hand-drawn isobars and mid-latitude cyclones, etc. This was done for May, and so May is not quite winter yet. It is getting cooler, but it's not winter yet. So this here is going to be an anticyclone here and an anticyclone here. Okay, and then all of these L's here are your low pressure cells. These are mid-latitude cyclones. You can see the cold fronts in just about all of them, and you can see the warm fronts in some of them over here. Okay, you can see that the pressure gradient is 996, and it gets higher as it extends outwards. Okay, whereas in the high pressure cell, your pressure gradient is 1000 and I think that's 26. Sorry, 28, 1028, and that gets lower as it extends out. Okay, so remember that the low pressure cell, the pressure is going to be lowest in the center, and it's going to get higher as it extends outwards. Okay, but so all these anticyclones here are called a family. So all these mid-latitude cyclones are called a family. If you have one, you can have one mid-latitude cyclone, or you can have multiple. So you maybe have a couple of cold days, up to a week, two, maybe a week and a half, and then like this, you're going to have a couple of weeks of cold, wet, windy weather. So another thing to notice is that with this anticyclone here, this high pressure cell here, these low pressure cells can't move over it. They're going to move around it, and that's exactly what they've done here. They have moved around it to reach South Africa. What I'll explain later is that in our winter, these actually move northwards. These high pressure cells move northward, but I'll explain that a little bit later. You can see that the interval here, the hectopascal interval, is 4, which it generally is. If you're never sure, or if you're not sure, always check the numbers on your isobars. As well as the pressure gradient. You can have a look at the pressure gradient here. You can see that your isobars are far apart, which means that it's going to be, if the wind's even blowing, it will be a very gentle wind. But when your isobars are close together, the gradient is steep, which means that the wind is going to blow quite fiercely. Okay. All right. This is a satellite image taken in 2020 in July, so it's winter. This is the mid-latitude cyclone over here that's going to extend across South Africa, and but here is a very big one. So this one would reach South Africa probably in a day after this, I would say, more or less. I'm not sure, but this would bring lots of cold, wet, windy weather, as it is quite big, and possibly even flooding. What's also important is that they can reach roughly 1,500 to 3,000 kilometers in diameter, and they can move about 1,200 kilometers a day. So they move quite fast and they can get quite big. All right. Very interestingly, I know it's rather off topic, as you have cloud formation here. You're going to have the equator is over here somewhere, and remember the warm air rises, so you're going to have warm air rising, you're going to have condensation taking place, and you're going to have rainfall. So you can see how green it is here, and you can see the clouds. Okay, moving on. All right, so this is how they move. All right, so you can see they move in they move in this direction. They move, and here, so this is the mid-latitudes in the southern hemisphere, and these are the ones in the northern hemisphere. This is hurricane tracks. In actual fact, this is not hurricane tracks. This is probably a tropical cyclone, which we'll discuss later. Okay, so this is how your mid-latitude cyclones move. All right, they always move west to east. Always, they're going to move westwards. They're going to move from the west to the east. All right. They're going to affect the coastal regions. They don't affect inland too much. Maybe a little bit of South Africa and South America, but not too much. Okay. So they're going to move west to east, and they affect the oceans, the coastal areas. Okay. Yes. All right. So what's important here, I did mention about a little bit earlier, I mentioned about the high pressure cells moving northwards. So when North America is experiencing summer, the pressure belts all migrate slightly northwards. So the polar high, subpolar low, subtropical high, equatorial low, etc., they're all going to move slightly northwards. And this includes the ITCZ. So in actual fact, the ITCZ is one line, but they've done it in two lines just to show you. So this is the ITCZ in summer in the northern hemisphere, and you can move slightly upwards, whereas in summer in the southern hemisphere it is moved slightly downwards. Okay, so in the northern hemisphere, when they're experiencing summer, the pressure belts have all moved slightly upwards, and this would include the mid-latitude cyclones. So they would occur over here. All right, the mid-latitude cyclones, and remember they are going to move slightly northwards in winter, and then in summer they'll move slightly southwards. So that's why we don't really experience mid-latitude cyclones in summer, because they've moved down. However, that is why we have them in winter, because the pressure belts have all migrated northwards. All right, I think that is about it for today. I hope that I was able to assist you, that you're able to understand it a little bit better. All right, so the last slide is where I've got my sources and my images.